3 teachers with different backgrounds have come to KS3, the school's science support service, to find out about teaching radioactivity.
I haven't taught radioactivity before. I'd be quite nervous in teaching radioactivity because of the dangers of it and because of my lack of experience and knowledge in teaching it.
I've been a physics teacher for, well, this will be my 5th year. I've taught radioactivity at GCSE in all those years, as well as teaching it at A-level.
I'm currently a PGCE student and I've just started my 2nd placement, and so I've got no experience of teaching radioactivity yet.
Radioactivity is something that people are naturally quite nervous about. They think it's dangerous, or they feel it might be damaging themselves, or they've got themselves in risk. However, when done carefully and safely, these experiments are completely fine.
Schools have been using radioactive substances in their laboratories for many years now, probably 30, 40 years, and they're extremely safe, very, very low activity, and provided they're looked after properly and used properly, there really aren't any problems.
I can open up the container using forceps and making sure that I'm holding them at least 10 centimetres away. I carefully take the lead lid off the container, I lift it out, stand it on the lead lid. I use the radioactive source, ensuring I'm not pointing at myself or the pupils.
How far back should the students stand?
Well, as we can see, you're about 1.5 metres away, and the same should be true when you're doing this with your pupils. Ensure there's a good distance between where you're demonstrating it and where the students are standing. When I've finished, I replace it back into the lead container, put the lead lid back on again, and ensure the source is back inside.
The most important thing is that the radioactives are kept secure, also that they're kept in a steel container, so that in the event of a fire, the radioactive material would be contained safely within that.
If you'd like more information on handling radioactive sources, speak to your head of science or contact KS3.
I always think it's important to start a topic with something to grab the attention of the children. And if your pupils are seeing something that they're engaged in and something which is a little bit novel, a little bit unusual, then you've got them. Now you're being silly, aren't you? I'm going to send you all off, and you're going to find a place to hang your balloon, and then when you get there, you're going to charge the balloon by rubbing it with the cloth, and we'll go back and collect it. Release the air out slowly as you let it down onto the paper. Here I've got a balloon that has not been inflated and has not been around the lab. I'm going to test it with the Geiger counter to see if I can get a count from it. As you can see, there is no count. Jill, would you like to pass yours across? And if we test it with the Geiger counter, we can notice that there's a significantly higher count.
That's quite a difference.
It is, and that's not really what you would expect from just hanging it in the corner of the lab.
So it's become radioactive over an hour then?
Oh, let's be careful. Has the balloon become radioactive?
It's just attracted the dust particles.
Good. Something stuck to it.
Yeah, so by charging it, what we've done is we've had the dust particles stick to it, and those have got the decay products of the radon gas that is found naturally in the air.
I think the balloon experiment really stands out because it's interactive.
Some everyday objects will register on a Geiger counter. The results may surprise the students. First is a domestic smoke detector.
And there's a slight count, and the reason for that is that inside the smoke detector is an americium source which produces alpha and a small amount of gamma. The alphas are stopped by the smoke if it's inside the chamber, which will then trigger the alarm to sound. So yes, it's radioactive, but not very.
That's quite surprising because you wouldn't expect a household product to be made with a radioactive source in it.
You could also try an old watch with a luminous dial.
Wow.
Whoa.
So, a very significant count there.
Yeah, the worrying thing is I'm sure I had one of those when I was a kid.
Although ionising radiation is coming out of the clock face, the radium-based paint is safely sealed inside. There's no contamination outside. There's no radioactive material where we don't want it.
In this demonstration, we're going to show the properties of ionising radiation. And to do that, I'm going to use a gold leaf electroscope. If it's not charged, the leaf hangs vertically downwards. To charge it, I'm going to use electrostatics, and I'm going to rub a piece of Perspex rod and then transfer that to the electroscope.
We can also charge the electroscope by using an EHT power supply set to 2000 volts.
I'm going to show that the ionising radiation from the radioactive source will cause the electroscope to discharge. Then I'm going to show the pupils that the forceps on their own have no effect on the electroscope, but when I put the radioactive source in, you can see that the leaf starts to fall down because the ionising radiation is allowing the plate to discharge.
This experiment shows how ionising radiation can allow a current to flow between two parallel plates.
The one on the left here is attached to the positive side of an EHT power supply, and the negative plate is connected through an electroscope back to the negative terminal of the supply.
Where would you get those plates from?
These plates are actually the tops of electroscopes, which I've connected into 4mm plugs, connected into a piece of dowling. It also has the bonus that this acts as an insulator from the high voltages from the power supply.
In this experiment, we're using a 5,000 volt extra high tension power supply, which some teachers worry quite a bit about. But in fact, if you're using one that's been supplied for school science use, it will be current limited to less than 5 milliamps, which means that electric shocks from it are harmless.
Now if I mount the radioactive source and aim it between the plates, the electroscope leaf starts to rise, showing that there's ionisation happening between the plates, allowing the charge to move for the electricity to flow around the circuit.
Why not use an ammeter?
You could use an ammeter. The trouble is that the amount of charge that's moving is very small. So measuring that as a current, you'd need a picoammeter. So we use the electroscope instead because most schools will have an electroscope and you can use that in the circuit. I've got my radioactive source at the bottom, allowing the ionising radiation to come between the plates. Each of those sparkles is representing an air particle which is being ionised. As we zoom in, the animation will show us each individual air particles and the ionising radiation coming from the bottom. It'll rip an electron from the surface, which is attracted towards the positive plate, and the ionised air particle is then attracted towards the negative plate and drifts sideways. This is happening all through the air particles, and what you can see is the ionised air will drift one way and the electrons are accelerated the other way, allowing the current to flow. If we zoom back out again, then we will see that this causes the electric current to flow between the two, which is what we've seen on the meter from the demonstration.
The cloud chamber uses dry ice which you can either buy or make yourself using a carbon dioxide cylinder.
The carbon dioxide cylinder you have to make sure you've got is called a siphoning cylinder. You can recognise it because it will say liquid withdrawal on the sticker and also have a white painted line down the side of the cylinder. To make the dry ice, we have to attach the dry ice attachment to the valve, like so. The nozzle has to face downwards and the nut is tightened but not over-tightened.
Dry ice can cause severe burns to the hands, so it's important to wear thick fabric gloves when handling them, for example, the sort that you can get from garden centres.
So if you'd like to put your safety specs on as well. When I open the cylinder, the liquid carbon dioxide will come into the chamber here. And as the dry ice is formed inside, you'll hear it starting to block the tube. Close the valve, and our dry ice is ready to collect. And you'll see inside the solid carbon dioxide into a plastic tray.
I hadn't even considered that I could make my own solid CO2 for use. I think I'll be going back and trying to see if we can acquire the apparatus for that.
We're now going to have a look at the cloud chamber. The first job is to put the alcohol around the edge.
Why use alcohol?
Alcohol is a dipole molecule, meaning that it'll be attracted towards the ionised air particle. When I find the source for the cloud chamber, you'll see it's mounted in a cork in a metal tin. I'm going to pick the source up by the cork, and I'm not going to touch the end which is covered with the luminous paint which contains radium. I carefully thread it through, and the cork also seals the chamber and stops the alcohol vapour from coming out. So now it's time to put the dry ice into the bottom of the chamber. I'm not going to pack it to the top, I'm just going to put enough in to cover the bottom of the chamber, and then put the sponge in to hold it in place, and attach the bottom and turn it to lock it in place. Once you've done that, you can turn the chamber back over. We can use the small wedges to ensure that it's flat on the table. And we're now ready to illuminate the chamber. You can then view from the top of the chamber to see the tracks produced by the ionising radiation.
The cloud chamber was my personal favourite. I thought it was really quite amazing to be able to see the activity of a single alpha particle and be able to visualise it. And I think the students would really enjoy that.
So here I've got the tracks from the radioactive source, leaving their trails as they streak through the saturated vapour. But on the small scale, let's follow one of those particles as it ionises the air on its way through. In slow motion, let's have a look and watch the alpha particle getting close to one of the air particles, ripping an electron from the outer shells, and you'll see them scattering away either way. So it gets close, it strips the electron and carries on moving. So as soon as the particle is ionised, the alcohol starts to be drawn towards it, clumping together and starting to form the track that we've seen in the cloud chamber. If we zoom out slightly from that, you'll see this is happening around every single particle that's been ionised, and that will leave a trail of the alcohol.
We've seen that radiation can ionise the air and the tracks that this can form. Next, we're looking at counting the individual alpha particles.
I'm going to connect the negative side of the high voltage power supply to the grill on the top of the spark counter. Underneath the grill, you'll see there's a thin wire which I'm going to connect to the positive side of the power supply.
Teachers sometimes find spark counters don't work very well. The main cause of problems seems to be dust. We recommend the spark counters are kept in plastic bags to avoid build-up of dust.
As I increase the voltage, in the end I will get a spark between the mesh at the top and the wire underneath.